This is Professor Monty. Today I'm going to show you how to do a two-sample t-test. So what we're doing is we're comparing the mean of two different samples. We don't know the population mean of either one. All we have is a sample of each population. So let's go ahead and take a look at the problem. Professor Monty has two statistics classes. One meets at 8 o'clock and the other at 9:30. A random sample of scores for exam number 3 provided the following results. The 8 o'clock class, 9:30 class, and we have a sample size of 10 from each class. Assume the scores are normally distributed and the population standard deviations are equal. At the 5% significance level, is the data sufficient to show a difference in the class averages? Okay, so this is actual data from my last test that I had in my classes. I did a systematic sample where I started randomly. I got a random number on my calculator of 2. I took the second entry and then every 8th entry after that. That gave me the sample that you see before you. I have 81 students in one class and 78 in the other class. Okay, so let's go ahead and do this. Again, it's going to be a two-sample t-test. It's a t-test because we don't have the population standard deviations. If we had each of the population standard deviations, then we could do a z-test. We are told that the population standard deviations are equal, but we don't know what they are. Okay, so we know it's going to be a two-sample t-test. So let's go ahead and start the test. We're going to start as we always do with our null and alternative hypotheses, and then we'll go to the calculator to get our calculations. So our null analysis, we have to assume, since we don't have any evidence yet, that the means of the two exams are equal. So mu1 is equal to mu2. I'll use mu1 to be population 1, which will be the 8 o'clock class, and then mu2 will be the population mean of the second population, the 9:30 class. The alternative hypothesis is always what we're trying to show. We're trying to show that the means are different. That's the question. So our alternative is mu sub 1 is not equal to mu sub 2. Okay, and from there, we're just ready to do our test. So let me go to the calculator. I'll show you how to do this on I have a TI-84. A TI-83 works the same way. Okay, so here's our calculator. We need to input the data. So let me go ahead and do that. We go into Stat, and then right away we go into Edit. So I'm just going to hit Enter. Now, notice I've already got list 1. I'm going to put my data in list 1 for the first population and list 2 for the second population. Now, the easy way to do this, to get rid of this data, I like to clear the data first so that if I enter my 10 data values, if I had more data values in there before and I forget to delete them, then it'll throw off my numbers and my answer will be incorrect. So the easiest way to do this is just arrow up to where it says list 1 and hit clear. Hit delete, that, get rid of the whole list. We don't want to do that. We just want to clear the entries. So hit clear. And then when I arrow back down, all the entries are gone. I'll just do the same thing for list 2 real quickly. So arrow up to where it says L2, hit clear, and then just arrow down and they're gone. Okay, so let's put in our entries. In the 8 o'clock class, I had a 76, a 74, a 79, a 93, a 37, unfortunately, a 61, a 100, a 58, a 98, and a 67. And again, we're making the assumption that these scores are normally distributed. We can't do the T. That's quite an assumption. Typically with grades, especially with grades with as high of an average as these are, you probably won't be normally distributed because you don't have a lot of upward mobility. Upward from, say, the average comes out to be around 75, 78, something like that. You can only go up to 100 as the high, but you can go down all the way to 0 potentially. And we already see that we had a 37. So it's probably going to be less skewed data, but we're going to make the assumption that it's close enough to normal distribution that we can use the test. Okay, So we have 88, 88, 69, 93, 89, 98, 76. So I'm just entering the data and then hit enter after each data value. 82, 43, and lastly 84. Okay. And so I've got all my data in there, do a quick lookup, everything's 2 digits except the 100, which is good, so I didn't miss a digit when I was typing in. So that all looks good. Now to run the test, we go back into stat, but then we arrow over to tests. I go to the left because it just loops around and gives me test. And again, I'm doing a 2-sample t-test. That's down at 4. You can arrow down there, or you can just hit the number 4. But if I arrow down there and then hit enter, it'll select it. Or I could just hit 4 and then I don't have to arrow down. Okay, we see it says a 2-sample t-test, and it's waiting for the stats, X bar sub 1, the standard deviation of the first population. We don't have any of those, we have the actual data. So let's arrow back to where it says data and hit enter, and notice it changes the screen. And it's expecting the data into list 1 and list 2. That's exactly where we have it. Leave the frequencies at 1. We'll arrow down from there. And the mu sub 1 is not equal to mu sub 2. That's our alternative hypothesis, so we're going to leave it there. Now, when it talks about pooled data, we pool the data if we can assume the population standard deviations are the same. In this case, notice we did say, and the population deviations are equal. Since we said the population standard deviations are equal, we can pool the data. If we can't assume they're equal, then we say, no, don't pool the data, okay? But that's what it's based on. Okay, so we're not pooling the data. And then I just come down and calculate, hit enter again. And I get a bunch of stuff. Notice the X bars are quite different. My sample mean for population 1 was a 74.3. Sample mean for population 2 was an 81%. So I say, hey, there's quite a difference in those sample means. Is that enough to say the population means can't be equal? Well, we base that on the p-value. So notice they do give us a t-value of negative 0.84. And I don't use that. I'd use that if I was doing the hypothesis using the critical. I'm not. I'm using the p-value method. Now that t-value is used by the calculator to find the p-value, but it's the p-value I want. So let's write this down. The p-value is equal to we'll go to 4 decimal places, 0.4115. All right, so let's go back to the board. Okay, so remember what we do is we compare the p-value to the significance level. And in this case, it says at the 5% significance level. So I go to see if that is less than or equal to this 0.05, which is alpha, which is my significance level. And again, remember what this is saying. 5% is my cutoff. I'm going to say, hey, I don't believe mu1 is equal to mu2. If it would happen so rarely, if I would get these sample results so rarely, that I don't think that's true. I don't think it could just be sampling error. Well, this says I would get my sample means this far apart 41% of the time. Well, that's not very rare at all. It's definitely not below our level of 5%. So I say, oh, that's not less than or equal to 5%. So I do not reject the null hypothesis. In other words, the data is not strong enough to say that we don't think this could be just sampling error. So we think, you know what, there's a 41% chance that it is just sampling error is why I got those sample means so far apart. So I'm not going to reject that. So when I answer the question, is the data sufficient to show a difference? I have to say no. No, the data is not sufficient to show a difference in the exam averages, means. All right, let me put this down a little bit so we can make sure we see the bottom of the. All right. So that's the idea. We're done with the test. And what's nice about this, we were able to come to a conclusion, and I will tell you, let me check real quick. The exam scores actually, my exam 1 average was a 78%. My exam 2 average was an 80%. So they were different, but they were actually pretty close. Obviously not very far apart. So, but based on our samples, this is the conclusion we came to. And it was the right conclusion, essentially. They were actually different means, but they were very close. Okay, so anyway, if you like this video, go ahead and subscribe to my videos. Make sure you look at my other video using this same data, talking about confidence intervals and how to interpret the confidence intervals for that. All right, well, that's it. So keep up the hard work, and remember, you can do this.